Alright, continuing on with the design of my motor drive. In this video I'll be focusing on the main power supply, which consists of this TPS54360 chip. Now the original schematic here was, so when I first put this circuit together, I used their tool to determine the parameters. Now we can set this to middle there, so we get the values that more resemble the, let's see, did I use these values? No, actually, maybe, I think I used, let's see, right, so what I did first was I used the highest efficiency setting, so I got values like this, I think. Let's just double check that. Yeah, 51.27 nanofarads and around 15k there. Let's see, 51.27 and 15k. Right. The only problem with this is that the inductor is 100 microhenries and 32 milliohms, and just to show you what it looks like. Let's see. PCB. This is what it looks like. No, thank you. Okay, this is not going on my PCB, and I had a little bit of trouble to find the inductor that would be suitable for this, which was of smaller size. And besides, any component that I find, which is according to their design here, it's probably not going to be exactly the same component. So I still have to go through the calculations, and I still have to double check that my design is going to be designed properly. So I chose the middle setting here, and this produced a little bit better schematic, which we can see what it looks like here. So we have this standard size 12 millimeters inductor, which is much better than using the huge toroidal coil. But there is still a lot of things that need to be double checked. For example, the compensation here depends on the ESR of this capacitor on the output. So if I choose a different capacitor, the compensation parameters here will change. And that's pretty much going to be the case. I'm going to have a different capacitor. The capacitor that I have right now is 100 microfarads, but there is an equation that will give me the minimum value for this capacitor. So I have to choose something that is higher, but I'm not completely tied to 47 microfarads. I can use 100 microfarads, but then I have to recalculate many of the parameters here. So I went ahead and I looked at the data sheet, and I looked at their examples. They have an application example here for 5 volts, and then I tried to replicate, sort of to jot down all of the equations that they used, and to convert it to MATLAB code, which I then could easily adjust to my design. Just to show what this looks like. This is the MATLAB code which I have now adjusted to my design, but this is pretty much the stuff that needs to be done in order to design this regulator. So this is not a simple thing to do. This is not like an LDO regulator where you just fit 2 resistors and you get your output voltage. This is a much more advanced regulator, but the benefit is that it's also very flexible. It can be used to, for example, produce split rail power supplies, and you have control over a lot of different parameters, which can be useful sometimes. So and also it can go to much higher frequencies than the cheapest regulators. So the ripple on the output becomes a lot smaller as the frequency rises. But the downside is that there's a lot of equations involved, and getting them right does require a little bit of attention to detail, because, for example, some equations use kilo ohms, and produce, or for example, they use kilohertz and produce kilo ohms on the output. But then in a different place, they use this RT value as a value in ohms. So generally, I try to keep to the basic units. So I keep the resistor values in ohms and frequencies in hertz. But that requires me to modify the equations a little bit. For example, I had to add 1,000 times. Just sort of course, I could simplify this equation, but I want to keep things as close as possible to the data sheet, but at the same time ensure that I have the correct scale on each variable. So I tested this with the 5 volts specification, which is defined in the data sheet here. And I got the values that they got in their calculations here. So then I updated the equations to better reflect my own parameters. And I'm going to go over each parameter here. So first of all, we have the parameters that do matter to us. And then we have the parameters that are intrinsic to this regulator. So let's go over the parameters. Our output voltage is 12 volts, and our input voltage is at most 60 volts. Our output current is at most 3.5 amps, and the resistor that I'll choose for the output, let's see, for the feedback is the lower side resistor for the feedback is going to be 10K. Now, it's quite possible that maybe I will not be able to find the high side resistor. The calculations that were from the designer tool, they used 10.5K resistor there and then 147K resistor there, and this gives exact division. Now, if I use 10K resistor, I may get an inexact division here, so I may not get precise output voltage. So maybe it's good to use 10.5K resistor anyway. But first I'll go over the parameters. I can update this to 10K and see what result it gives me. Now, this is the DC resistance of the coil, and it's specified in the data sheet of this coil that I chose. I had to update this coil from the previous component that I used in the previous video because that component had a much too low current, and for some reason I missed that detail, so I still use that component, but it wouldn't work in under higher currents. So I had to replace this with a 33 microhenry higher current inductor. It has the same footprint though, so I didn't have to change that many things. The next thing is so when the input voltage rises, this parameter specifies the voltage at which the regulator will power on. And it has to be higher than the output voltage, and it has to be higher than the minimum input voltage, which is calculated using the equations here. So I chose 17 volts. And then there is another voltage that specifies when the regulator will power off. So this calculates the resistor divider that goes to the N pin, but the N pin can be left floating because it has a pull-up resistor inside the chip, which will power on the regulator whenever the voltage reaches, I think, the minimum input voltage, which is calculated using the equation. But for the sake of the calculation, I specify the minimum startup voltage 17 volts and the minimum voltage before it powers off at 14 volts. This is LO is the inductor, which is 33 microhenries. DCJ, that's the capacitance of the junction of this diode. This is also from the datasheet of the diode, and CDBC 5100 has a junction capacitance of 380 picofarads. This is the output voltage ripple in percent, or rather just as a number, sort of as a fraction of the output voltage. So I set this to 0.5%, just like the value that they used in their application. This is my output capacitor. I set it to 100 microfarads because I want to see what will happen if I reuse as many components as possible. And this is the ESR of this output capacitor. Now I may actually add another capacitor here to lower the ESR of this output circuit, and I have to check the ESR of this capacitor because the 25 milliohm is just the same value that they used in their calculation. So I have to go and check the ESR of this capacitor, and it may be the case that the ESR is not going to be specified in the datasheet. Sometimes it isn't. But let's see what the datasheet says. So I'm going to go ahead and move the datasheet to this window here, and we'll see what it says about the ESR of this capacitor. This is an electrolytic capacitor. Let's see. I think it's an aluminum capacitor, but yeah, it is an aluminum capacitor, and the ESR is maybe it's not specified. Let's see what it says. Series rated voltage, date, the ESR. So this is the ripple current on the capacitor. Which I think may need to be higher than the inductor ripple current. So it's quite possible I'll have to choose a different capacitor. Let's see, we have 25 volts and we have 100, so we have 300 milliamps of ripple current. This is not optimal for this case. So I think what I'll do is I'll actually keep this. Let's see. I'll actually keep this at 100 for now, and I'll run this script to make a calculation for the minimum capacitance that has to be on the output. And the minimum capacitance is going to be determined by the minimum and maximum. So this is maximum, and this is minimum output current. I think so. When I'm designing this this board like this for the revision A, I don't actually know the minimum and the maximum output current. That's going to need to be measured. So what I'll do is I'll just let's see. I'll just keep the values that they have used in their application, and maybe I will I'll first try to run it with these values, and then I'll try to reduce the low limit and maybe increase the high limit a little bit and see what happens to the calculations. But for now I'll keep it at 2.6 amps and 0.8 amps. And this is the switching frequency, which also needs to be chosen based on the maximum switching frequency that can be used based on the equations. And this is the input capacitance, and this is the voltage drop of the diode, which is this D12 diode there. These parameters are intrinsic to the regulator, and they're all described in the datasheet. And then we have the equations. So let's see. First we have let's actually run the script. So what we get is that our let's see. Let me bring up the datasheet of this TPS chip so I can go over every single parameter here. Yeah, so the equations for the, let's see, I think it's in the feature description here. So the minimum input voltage is determined by the output voltage, the voltage drop of the diode, the DC resistance of the inductor, and the output current, and also some intrinsic parameters, which is here the drain source resistance of the high side MOSFET, which is specified in a table in a different place in this datasheet. So our minimum voltage is calculated to 16 volts. Which is not surprising because our output voltage is set to 12 volts, so a minimum input voltage has to be higher than 12 volts because this is not a boost converter, this is a buck converter. The maximum output voltage is calculated by let's see, it depends on let's see, it depends on this D max, which I'm not actually sure what it is. Let's see, D max. I haven't been able to find this D like if I search for just D, I get like every single D in this datasheet. So I wasn't able to find what D max actually means. So I used the value of 0.9 in my calculation. This equation calculates the maximum output voltage. And the output voltage can overshoot in case, for example, the load current suddenly increases. And what this means is that so it's very important to take care of ensuring that the output circuitry is able to handle these overshoots. Because if you have, for example, a circuit that expects, for example, like a processor module, this is a problem that I had before when I designed a 3.3 volts supply using a buck converter similar to this one. And just any buck converter where you have a switching any kind of switching regulator, and what happened there was that when the current suddenly increased during startup, the voltage increased beyond slightly over 4 volts, and that was too much already for the module. Like most circuits, they can handle voltages up to maybe over 4 volts. But in this case, the regulators on that module were not able to handle anything above 3.6 volts. So it was very important to keep the voltages down. And the reason this happens is that the switching regulator works kind of like a PID controller, but for the voltage. So when the current rises, when the load is increased very suddenly, then the voltage momentarily can overshoot the target voltage before it then stabilizes again. So it's important to calculate what our maximum output voltage is going to be. And in this case, it's going to be slightly over 14 volts. And it also depends on the input voltage, on the minimum input voltage, on the maximum output current, and on the resistance of the internal MOSFET, as well as the diode voltage drop. And the DC resistance of the inductor as well. So in this case, this is going to be fine because this regulator can accept up to 17 volts on its input. So anything that goes out here, that if this input goes to 14 volts, nothing is going to break here. But it's also important to make sure that anything that is connected here can accept voltages of 14 volts. But that's not a big difference, and usually any 12 volt circuits cannot accept 14 volts because they're created for automotive applications where you have 12 volts supplies, and in the car the voltage can easily rise to 14-15 volts when the car is running. So moving on to the next parameter, which is the high side resistor in this voltage divider, which specifies the output voltage. And you remember I changed this to 10K, and when I did that, my high side resistor changed to 140K. Let's update this. Let's see if I use 147K anywhere else. 147K. Yeah, so I'm using the same resistor. Let's see if I use 24K anywhere else. Okay, so I'm not using 24K. So maybe let's see. So this circuit requires three components that are non-standard. If I change this to 10K, then I only require two components that are not used anywhere else, which is a small benefit. So I'm going to do that. Right, or maybe not actually, because there is a specification for the power dissipation here. So we need to have resistors that are capable, that are rated at 125 milliwatts according to their recommendation here. So it's probably a good idea to follow this recommendation. Let's see what power ratings we have. So 603 is rated, let's see, is it that we need 805 all of a sudden there? 125 milliwatts is 805. Okay. Interesting. I wonder if there is any calculation that specifies that. I wonder what kind of current will flow into the feedback pin here, and whether so maybe it's that. Let's check the waveforms actually. This is what happens when current is when load changes. All right. Like to me, it seems that the power dissipation here is not going to be an issue, but I still wonder why the recommended schematic uses such large resistors. Let's see if I can find anything on that. Let's see, so we have 12, or rather no, it's, let's see, we have 10K divided by 140 plus, right, 150. So that would be the division of voltage times 12. Maybe it's, All right. So the input here should become. It seems like the input voltage here should be targeted at being 0.8 volts, which is the internal reference as well. So let's see. So we get 0.8 volts across this resistor, and the current that will flow then. Let's see. I mean, this is going to be in the order of microamps, because if we have a current of 3.5, or let's say we have 4 amps here. And if we have the voltage across here of 12 volts, then we can have like this, 12 divided by 150,000. That would be about 80 microamps. Right, okay. So we have 80 microamps, but then we have see, so am I doing this right? So around 1 milliwatt across both of them. So this seems like there is no issue in terms of any power dissipation here. So I'm not sure why they use such large resistors in the recommended schematic. Could there be something I missed? Hmm. 402 can take 62 milliwatts. This is interesting. I should be able to use 402 here. I don't think this would be an issue at all. So if I then have 0.8 volts on the bottom resistor divided by 10,000, which should give us the current, and then times 0.8, so I get right. So this would be 64 microwatts of power dissipation in this resistor. I don't know, maybe I missed something. Maybe somebody can point out why these resistors are specified as 805 resistors in the recommended schematic. Anyway, I'll change this one to 10K. This one will need to be 140K. Actually, there is a 135K. Let's see. So I do use 135K. Do I? I think I had something that is close to that at least. $137K, and I do have 135, but I'm not using it apparently. Right. So I'm using 137K for the voltage sensing there, which is actually quite interesting. We could use that. So the voltage will be slightly, let's see, the voltage will be slightly higher than 12 volts, but it will be so small difference that it won't matter. And I could calculate exactly how much higher it will be. Change this to 137 and 402. No! It's so annoying that KiCad closes the window. Let's see. It's a large K there and 137 there. Let's click validate first. And so the output voltage will then be, if we have 0.8 volts here, so let's see, we have 0.8 equals 10 divided by 147 times 12, which should be our, right, so 12 times like this, which would be our voltage here. Should be 0.81, and we can take 0.8 divided by, so we can say 0.8 divided by 12, and times no, so we need to find out that will be our value that we need to calculate. So this would be 0.8 divided by 10 divided by 147. 11.76 volts would be the output voltage if we use this configuration, which I think is perfectly fine in this case. I'll just make a note here. So, the undervoltage lockout, I'm not going to be using them for now. Startup time is calculated to 1.7 milliseconds. RT is, right, so this is, let's see, we need to have, this is the timing resistor. So I'm going to add it to our calculation, to our printout here. have RT, and we have the maximum absolute maximum frequency, or absolute maximum switching frequency, 1.58 megahertz, and shift. So the frequencies need to be lower than the switching frequencies need to be lower than these frequencies, and I choose here the same value that they chose for their application, 600 kilohertz. And minimum inductor is 1.52. Let's see. $15 microhenry. This would be, I think, yeah. And I chose 33 microhenry, which is within the limit there. The output ripple, half an amp. Inductor should be rated at least 3.74 amps, which is correct in my case. I have an inductor that is 4.2 amps. The minimum, let's see. I think I commented out that line. So C out needs to be, yeah, we can do like this, C out min. So minimum output capacitance has to be 42. Would that be, let's see. I think that will be 42 microfarads. Let's see. Did I get all the zeros right? No, it's 420 microfarads. Wow. I was a bit surprised it would be that many. That was a large capacitor. I'm going to check their design here. I think something is wrong here, because their design uses a much lower capacitor in the datasheet here. Output capacitor. Did I get some zero wrong there? So this should be 7.8. Yeah, 7.8. Oh, okay. I think I did something wrong here, because I think let's see. I think this should be min. Right. Yes, this should be the minimum of all of the. Of course, it should be min. So if I do like this, then I get minimum output capacitance of 1.68 microfarads. That's much better. So I'm using 100 microfarads, which is well within limit. And what we can do here actually is we could add a 2.2 microfarad capacitor as well. Let me just move this out a little bit. And the reason for doing this is that this would be a ceramic capacitor. It will lower the ESR a lot, and also it's not possible to determine the exact ESR, which we do need for our calculations for the compensation. But we don't know the exact ESR until we have the components. So it's kind of like a chicken and the egg problem. I have to design something that has the best chance of working, but if I'm going to fine-tune it, then I have to do it later after the board is manufactured. So I'm going to add this capacitor just for the sake of lowering the ESR on the output. So what will happen here is that we'll have a lower, we'll have an ESR that is lower than the lowest ESR of these two capacitors, and we'll have a capacitance that's slightly higher than 100 microfarads. But because capacitors degrade, we don't need to really take that into account. So this capacitor will probably degrade to like 90 microfarads or lower than that. So I'm going to just let's see. I'm going to just add this capacitor here, and I'll use the same value for the ESR as they used, like 25, I think, milliohms for now. So let's see what we have next here. Let's see if I find any other problems here. So maximum ESR is 125 milliohms, and I think by adding this capacitor I do ensure that it's below 123 milliohms. So I think I do ensure that it's below that, and the ripple current is 139 milliamps, which is good actually, because let's see what we had here. Where did I have this capacitor? There. So at 100 microfarads, we have a current, let's see, 16, is this? No, 25 volts. So it should support 300 milliamps, which is within limit here now. That's good. Power dissipation of the diode is 2.68 watt, which is handled here because this is a 100 volt 5 amp diode. So next on the list is I think this is the RMS current. ICI RMS, what is that? Could this be some current on the where is our max? Out and then yes, yeah. Okay, so IC out is the IC out RMS, and then we have the ICI RMS. So this is for the input capacitor. Actually, I wonder if it's really necessary to have this capacitor. I want to check their webbench and see here. So they specify that this capacitor should be 47 microfarads. In which case using 100 microfarads is fine, because having a little bit more is just better because they degrade over time. But according to my calculation, I get minimum value of I think somewhere above 1 microfarad, which is a bit of a large difference between this value and 47 microfarads. And it's not clear to me really why that is the case. Why did they choose such a high capacitance there? Maybe because of the same reasons. Maybe they want to have a higher margin between the minimum capacitance and the capacitance they use. Let's see. So our ripple current ends up being 1.5 amps, and the voltage ripple would be 6 millivolts, which is very negligible. But 1.5 amps, I think. So the next question is whether the input capacitor should be rated at current ripple of 1.5 amps. Requires high quality input decoupling capacitor with at least 3 microfarads of effective capacitance. Right, so we do need an input capacitor, and we cannot use this capacitor. Okay. So what I could do here is I can keep this capacitor. Originally I thought that I would actually move this behind this current sense resistor, but I can keep this capacitor where it is. The main purpose of this capacitor is to provide any extra current when the supply voltage may drop way below the actual nominal voltage on the supply. In case the break is engaged, for example, then the supply voltage is shorted to ground over the break resistor. So this capacitor, I'll keep it there, but I have to add another capacitor here, which, as they say, is X5R or X7R, and I'm probably going to go with X7R because they're pretty much the same price as X5R. And let's see, capacitance variations. For example, for this example design, ceramic capacitor with at least 60 volt voltage rating is required to support the maximum input voltage. So 2.2 microfarads. Do we have the input capacitor somewhere? How do we calculate the input capacitor? Okay, we just choose the input capacitor basically, and we get our voltage ripple there. So let's see what we have in terms of input capacitors. What can we reuse in this circuit? I think I do have the capacitors I could reuse, and I got them here. So I have several ones here. I have the 220 63 volts, and I have 2.2 100 volts. So I'm going to use 2.2 100 volt capacitors. And that would be pretty much just like what they used in the example. Let's see. So I'm gonna have to move this out a little bit. Okay, very important to make sure that this is connected. And then I'll have to redo the calculation for the voltage ripple, which will kind of in this case be the worst case. Oh, no, what am I doing? I'm doing something really stupid here. Let's see. Shall I move them? Shall I go just like this? That's a bit ugly. I think maybe like this. Actually, yeah, what I'm going to do is move them here. Right. And I want to make the text smaller. Can remove this. I can actually do like this. 282, 100 volts. That's one way to make the text smaller, so that the schematic looks better. So, so then we can update this input capacitor C in to be 4.4. Yeah, and then I get the voltage ripple of 331 millivolts, and the current on the capacitor is 1.5 amps, but since this is ceramic capacitors, they're going to be fine with that. We could check if the datasheet says anything about that. Let's see. This is just testing, so 50 milliamps for a testing situation. Yeah, they don't even specify charge discharge current, but let's make sure that this is. Does it say what type it is? Probably says in the product code. So let's look at the product code. Can I? Okay, I'm gonna do like this. X7R 1210. Okay, cool. So we got that, and this calculates this voltage ripple on the input, which is going to be smoothed out by this capacitor, by the way, anyway. So let's see. And then we have the frequency pole and frequency 0. And this is determined by the output ESR on the output capacitor. So this is kind of, we don't really know what the value will be exactly. And I think FCO is something to do with the frequency. Let's see. FCO would be the compensation frequency, and then we have to choose the lower value, I think. Use the lower value of 46 and 47. Okay. So we use the lower value, which in this case is 5.4 kilohertz. And then we compute R4, which would be the resistor that is placed in series with this capacitor, in this case R37, and then we get C18. Let's see. So let's look at the printout here. We get 12K for this resistor here. So we could set one of them to 10K and the other one to maybe 3K. If I have anything that's 12K, I've got 24K, I've got 3K. Yeah, so I'll just use 3K. And that's good because I don't have to change any, I don't have to remove any components, and I can reuse a lot of the components. And then we have the C-comp, the larger one of them, which would be the C18 in this case, would have to be 28 nanofarads. And the other one would have to be 200 picofarads. I don't think I have anything that's 200 picofarads, or in any sort of picofarad range for that matter. So I think I'll have to just find a capacitor that's 200 picofarads. And I'll keep this one at 27 nanofarads because that's close enough. But let's see what we can replace this one with. Yeah, it would be basically two 100 picofarad capacitors. I think. But I don't think I use them anywhere in this schematic. Or actually I do. Well, that was very fortunate. Okay, so I have the 100 picofarad capacitors, and that means I can just reuse that component in this schematic as well. So I'll copy this one and just have two of them like this. And then we have R40, which would be the RT, the timing resistor. That has to be 161K, which means we could reuse 147K. So I think we'll have a little bit smaller, a little bit lower frequency, but we can also calculate that. So we have see what we have. Yeah, 147K, but then, okay, so 147K is 603. I don't need 603. I need, can I search with a wildcard? Yeah, cool. That was possible. Let's see if I use 137K there. So what implications does this have on the regulator then? You can easily see that. Let's see, RT chosen. Let's see. And then we have I wonder if I need to adjust anything else here. Right, so I think this should be fine. So we get a lower compensation resistor. Or do we? No, I think I had the same one there. Let's see. That is not affected at all. But I think RT, right, yeah, because I forgot to specify. Yeah. So this is a necessary step. So we get 700 kilohertz switching frequency, and then we have so what changed here? Let's see where switching frequency is used below this. Okay, so it affects the minimum inductance, so we have to check this. 1.29. Yeah, 12. Okay, so it goes down a little bit, the inductance there, and the ripple is affected as well, but not by much. And the inductor peak current, and also the minimum output capacitance, C out min, which is like 1.2 microfarads. So basically the limits are changed, but considering that we have chosen components with a large margin, we don't need to change any components after making these adjustments. Right, so I think this is getting much better now. One last thing though is that I want to add, because if something goes wrong with this regulator, this is a switching regulator, so it switches the input voltage on this output pin. It goes up and down, up and down. So there can be a corner case where this voltage actually goes and actually gets stuck at the input voltage, which would be 48 volts, for example. And I had this problem before, but the cause of this problem was that I mistakenly chose a diode that had a voltage rating below the supply, the required voltage rating for running at a certain supply level. So what happened was that the diode latched up, and things got really out of hand. What I need to do here is make sure that we have a fuse right here, so that if the voltage rises beyond something like 14 volts, when this diode starts to conduct, then this fuse will go. And this fuse does not need to be any large fuse. It can be a small SMD fuse, because under normal circumstances it will never fire. And we can set the fuse value at 4 amps. Come on. Oh, be back soon. Okay. Can we search an octapart then? Yeah, this is not gonna really give us... there's so many fuses that I really want to just search on Mauser. There we go. Okay. Fuses. Let's pick something between 4 amps and 5 amps. Surface mount fuse without fuse clip, without fuse holder. Yeah. And not a glass fuse. Ideally, I'm thinking about something that is like a fast-acting ceramic fuse or something like that. So something like this. I'm just gonna check the prices. Is there some option I can choose here for fast acting? Let's see, fast blow. Yeah, awesome. Amps, and what is the package here? 805. And this one is 603. Yeah, let's go with 603. No. Okay. Let's not go with that because they're not available. This one is 603. let's go with this one. 603 4 amps fuse. .63 volt DC. Okay. Which doesn't matter in this case because we only have 12 volts. Fuse. There we go. I think I'm pretty happy with this right now. I may need to do some minor adjustments, but I think that my MATLAB script has hopefully produced the correct values. Yeah. So what's left here is to just document this design beside the schematic, so that it's apparent what settings have been used to calculate the values, in case they need to be changed later. That's it. That's it for this video, and thanks for watching, and I hope this was helpful to you in some way.